during stage, are you all ready? You all have this, the question there? Yeah. The Saturn V rocket, during stage 1 of its flight, reduces its mass from 2.3 million kilograms to 0.48 million kilograms in a time of 2 minutes and 42 seconds. Let's just draw that. So, there's the rocket. Okay, and it has its fuel here. And a time of, what was the time? 2 minutes? And how many seconds? 42 seconds. This fuel gets burnt off. How much of it gets burnt off? Well, let's see. Mass of what's burnt off. How much fuel did it have at the beginning of this story? 2.3 million? And how much did it have at the end? Minus 0.48 times 10 to the 6 kilograms. So what's that? That's 1 point... what's 2.3 minus 0.48? What's that, please? 1.82, is it? So 1.82? Yeah? Is that right? Okay. 1.82 times 10 to the 6 kilograms. Okay. So, and I tell you the speed. This fuel comes out at a speed of 3124 meters per second. Okay. So does anybody remember then what is the acceleration of the rocket? Okay. So Newton said F equals ma. So that means A should equal F over m. Now, problem. What is the F? We have a formula for the F for rockets. Does anyone remember? Does anyone remember this? The formula for the force, the rocket?
Gas times mass of gas per second.
Yeah, the speed of the gas, which we know, multiplied by how much gas comes out per second. Now, do we know how much comes out per second? No, we don't. But we know how much comes out, and we know how long it takes to come out, so we could work it out. So if just by dividing, yeah, so if I just have up here 1.82 times 10 to the 6 divided by, what's 2 minutes and 42 seconds? Is it like 60 and 60, 162 seconds? Yeah. Now here's something interesting. What do we use for the mass of the rocket? What do we think? Kim, what are you thinking? Ah, no, you have an idea. I can see it here. Are you sure? Okay. Mass, do you have any ideas what we could use for the mass?
The fuel.
Which number? Yeah.
2.3.
2.3. Good? Not this. Which one? The 0.48? Not this one?
Divided by 2.
That's the one. You see, what's happening with the rocket is as it's moving, it's losing fuel. So it's losing mass. So what number should we use for the mass? Well, not the mass at the beginning and not the mass at the end. So maybe we should use the average mass. That's usually what we do in physics. When we have something that's changing, we can use the average. Okay? So that would be 2.3 plus 0.48 over 2 times 10 to the 6. And we can calculate this. When you're ready, if you can calculate this, that would be great. Yeah.
Whose number under the first 1.82?
1.82 times 10 power 6 over 162.
162.
Yeah. Do you have an answer for me, Matt? No?
25.2?
25.2 seems reasonable, yeah. But my answer is 15.4. Now it's possible my answer's wrong.
That's 1.82, right?
Yes. What you get, George?
How do you get 25.2?
Ah, is my answer wrong? That's terrible.
So what you get?
Oh wait, no! It's not. Forgot something. You all forgot it too. So, it was here. We're still asleep. We said, from this, the heck? From this, acceleration equals F over M, yeah? So it's F over M, but there's two forces. There's the force up from the rocket which we calculated, but also, what other force?
Drag.
Not quite drag, but weight. You see, we forgot to consider the rocket has a weight. If you look at the picture here, there's a force here, and there's a force here. So we have to subtract the weight. I don't think you have to rub out anything, because I'll just, well, maybe this part, just minus mg. Okay, so I just make my fraction a little bit bigger. Minus mg. And we'll use the same trick by using the average mass, okay? So that's a 2.3 plus 0.48. 0.48. So if we make that small extra piece to the numerator, can you see that?
3 plus
0.48. 0.48.
24.24?
Is that the new answer? Did you put in the minus here? And did you put in 10 to the 6?
how we know the 162?
Ah, that's the 2 minutes and 42 seconds.
Oh.
It's the time.
Okay.
Yeah. And you have the G, 9.81? George, do you?
So in every single case we have to calculate the average mass?
In cases where the mass is
No,
changing.
like here for example, because even on top, like both of them have to be the average mass, not just the one in the denominator.
Yeah, both. Yeah. Got it, Siva?
No, I got a really weird number.
What you got?
Negative.
Yeah, that's weird.
I do it again.
Maybe you need to put brackets here. You got a calculator, Kim?
Yeah, I've got it. I don't know. Is it
Yeah, I can read it to you. Which part? Start, middle, end.
middle?
2.3 plus 0.48 over 2 times 10 6 and G.
That's 0.48.
Yeah.
$15.4. 4.
Ah, yeah, that's the right answer. 15.44 meters per second squared.
I still get 21.
Mm. Do you want me to have a look at your calculator to see what you typed in? Can you pass that up to me, Matt? But try not to delete anything. Let's see. Mhm. Mhm. Looks okay. No, I can't think it's the calculator. Ah, here it is, Siva. Instead of writing 2.3 plus 0.48, you wrote 2.3 times 0.48.
24 times 20.
No, that's not it.
No?
Now it's correct. Ooh,
I'm sorry.
24 plus
Okay.
24.
Ah.
Where'd you get the 72 there?
Wait, what?
That one? Minus.
Get that one from bracket. Then one plus four. Then plus the bracket. Then times. And everything. This bracket.
This?
Alright, do it step by step. Right, got negative. Because I just put all the
No, you can't. No. It's definitely 15.44. If you're not getting, it's definitely that. If you're not getting it, then you've done something wrong. Now, that's a plus there, okay? Yeah, you know that already.
It's a G minus.
No, just 9.81. I already have the minus here. See?
Yeah, but then why wouldn't the G be minus?
No. The G is 9.81. We say the acceleration is minus G. The minus, we never put the minus in the value of G. We always put it outside the value of G. You know, which is what I actually did here by writing the minus here. I've already considered it. You know.
Oh.
But
The times then only minus. Right. No.
Hmm?
No, you just subtract. You have to minus.
Well, he has a calculator that's difficult to use. Is this okay now? Are we sure? Shall we do the next one, number 5? Matt? George? Will we do number 5 now?
Okay. Like you get it, it's just at the calculator.
Yeah, no, you trust us. This is the answer, 15.44.
You multiply plus, then only minus.
I have no idea with that calculator. I have no idea.
Here, I just minus. You don't multiply anything.
You know, what you could do, Matt, is you could buy a Casio calculator.
What's a calculator?
Yeah, but it's old one.
Sorry, you could buy a newer Casio calculator. Alright, let's look at 5.
The only funny thing was, I have warned you. The only
Is that all that's left?
Yeah, that's all I got.
Okay, 5 now. Now don't worry about it, Matt. It's definitely 15.44.
Wait, I got it.
You got it? Okay. A very small rocket is at rest. The mass is 100 kilograms. Now, in the question I tell you, the mass of the rocket is 100 kilograms and 90% of it is fuel. So how much of this 100 is fuel and how much of it is rocket?
10 rocket.
10 rocket and 90 fuel. So, you know, we imagine maybe the rocket is 10 kilograms and the fuel here is 90. Now, the gas comes out at 9 kilograms per second at a speed of 100 meters per second. What is the weight of the rocket before it takes off? Okay, so the weight of the rocket before it takes off. This means before you turn the engine on. So the weight will equal mg, which equals 100g, which equals 981 newtons. Okay, is that part okay? Yeah? What is the reaction force before it takes off? So if I draw a little picture here, B, there's the rocket. It has a weight and a reaction force. And before it takes off, the R should equal the W. Okay, C. What is the thrust at the moment the engines are fired up? So you turn the engine on, what's the thrust? This is the force from the engine. And what's the formula for that? For the rocket? Mass per second times the speed of the gas. So how much gas comes out per second in this story? 9. And how fast does it come out? 100. So it's 900 newtons. Is that okay so far? Yeah? Okay. D. What is the reaction force at this moment? So there's the rocket. The engine gets turned on. There's 900 newtons fired this way. The weight is 981 newtons. And so the reaction force would have to be 81 newtons. Why? Well, because the reaction force plus the thrust has to equal the weight while it's sitting on the ground. Okay, so the gas, the engine fires up, flames come out, and you have 900 newtons of thrust, and so there has to be 81 newtons from the ground reacting up. Now, you might think this is a little bit strange because this leads us to the next part. Why doesn't the rocket take off at the beginning? What do you think has happened here? Why, in this picture, why isn't the rocket taken off?
It's just as accurate in the...
Yeah, the thrust isn't big enough. It's only 900. 900 newtons is less than the weight of the rocket, which is 981 newtons.
So it means it would need to be greater.
It would need to be greater. Yeah, exactly. Okay. But then part F is, when will the rocket take off? Now the thrust doesn't change. It's always 900 newtons up. There's a 900 newtons up here, but eventually the rocket will move. And why do we think that is?
When the fuel decreases to the mass.
That's the key, yeah. Because the fuel is being burnt off, eventually it'll be light enough to lift. So let's try and figure out when that is. Can I scroll down a bit more? Yeah. So if I draw a little table here, let's look at the time. So the time at the beginning, the mass of the rocket, what am I doing, sorry? Time, mass. So right at the beginning, the mass is 100 kilograms. Okay. Then after 1 second, it burns 9 kilograms, so you're left with 91. Then after 2 seconds, you're left with, 82. Now let's calculate the weight. It was 981. What's 91g, please? 91 times 9.81. 8. So 893 then. Yeah. So anyway, but my key point is, if the thrust is 900 newtons, when has it become big enough to take off? Only after 1 second. After 1 second, you have more thrust than you do weight. So it'll start to move upwards now. Okay, so The answer is after only 1 second. How long will the fuel last? How much fuel does the rocket have? 90 kilograms. And how much comes out per second? 9. So how long will it last for? 10 seconds. Because you have 90 kilograms, 9 kilograms a second, so it'll last 10 seconds. Okay, will I just pause for a minute before continuing? Yeah, because the last part is very hard. Very, H, yeah, very hard. Yeah? Oh, look at that rain. Again. Okay, just let me know when you're ready for H, because there's lots of steps in H, so. Yep. Yes, no, Seaback, Kim? Yep. George? Yep. Okay, let's have a look at H. Right, so let me just draw what's happening here. So, here's the ground, here's the rocket. Rocket fires, shoots up, and then after 10 seconds it runs out of fuel. So let's see what happens in the first 10 seconds of its flight. What is the acceleration upwards? Well, when it's moving up, here I'll just draw it here. When it's moving up, there's two forces. There's a T force up, which is equal to 900 newtons, we said. And what's the other force acting on it? The weight. Now, weight equals mg, but there's a small problem. The m keeps changing. So we should use the average m. So what's the mass at the beginning? It's a full 100. And the mass at the end is 10. So that's 55 times 9.81. What's that, please? 55. 539.55 newtons. Okay, that's 55 G. Right, so Newton said F equals ma. So A equals F over m. And there's two F's here. There's the 900 going up and the 539.55 going down. And the mass is on average 55. So on average, what is the acceleration upwards, please? That's a 55, not 5.5. About 10 or 11, isn't it? What you get, Sebra?
6.5.
Yeah, okay. 6.5? 6.5 exact?
6.5.
5.5. Meters per second squared. Is that okay? So what's happening here is that the rocket is accelerating up with this acceleration. Okay. So let's just do this as a UVATS problem. U, it starts at rest. V, we don't know. A, we do know. It's a plus because it's going up of 6.55. It's positive. It's going up. UVA, T, we do know. It's 10 seconds. And S, we don't know. And I would like to calculate the S, and I'd like to calculate the V. So what would be the easier one to get first? The V. V equals U plus A T. So the V is 65.5. And now let's get the S. S equals U plus V over 2 times T, which is 10. So what's that, please? Like about 300 and something? 327.5. Okay. Now, what happens after 10 seconds? The rocket doesn't just go up for 10 seconds and then fall straight down. What happens after this 10-second moment? What happens next is my question. Goes up, yeah. Will it continue going up forever? Not quite, because the engine is turned off. So describe what would happen to its journey now. So no more fuel. The fuel is gone. So what's going to happen to the rocket? Yeah, immediately or eventually? Eventually, yeah. It's going to go up a little bit. Then what will happen? It'll stop, and then it'll fall back down. Because it's starting to, in this part of the journey, it starts to slow down because it has no fuel left. Okay, so this is now another UVATS problem, which I'll just squeeze over here. So the U is what? 65.5, because it's the V from the previous journey. Yeah. Okay. Let me just. U is 65.5. What's the V? 0. Now, what's the A? Think carefully. What's the A? Yeah. It's because it's free falling. The T we don't know and don't want to know, and the S we don't know and want to know. So we want to know the S. So what would be the easiest thing to give me the S? Maybe V squared. V squared equals U squared plus 2A S. So the S is whatever 65.5 squared over 19.62 is. $220. I was close. 218.6. So our final answer is that maximum height would be 327.5 plus 218.6, giving me roughly. Yeah, I wrote 547 in the book. I think it's because I think in my book, last year I just said, oh, it's 100 plus 0, but I'm being a bit more accurate because we still have the 10 at the end. So I think 546 is probably a little bit more accurate than 547. Oh, do you know what it was? No, I remember now. I started at 100, but I think in my video I really started at 90 because it doesn't begin to move until it's at 90 kilograms. So because of this small difference, it affected it by 1 meter. But it's not really a big deal because we're approximating to begin with anyways. So, you know, there's kind of an acceptable sort of plus minus 1 meter at the end here anyways.
Can you scroll up? I just want to see that.
Huh?
Yeah, just do the rocket up there.
It's an interesting question.
It will be in the
Real test?
No.
Already?
No. I'll tell you which one I saw in the test before.
ABCD?
No, no. 1, 2, 3, 4. Not question 4. Yeah.
Okay.
Right. When you're ready, let me know, and we can do something else. What's next, so, folks? Which lesson?
Principle of moment.
Oh. Yeah, okay, cool. Which one?
5.
5, sure. Principle of moments. Got that? Page 5. Let's have a look. Okay. 100-gram meter stick. It has 2 strings, which are 10 and 20 from the end. So here there's a string, and this is 10 centimeters. And here's a string, and this distance here is 20 centimeters. What is the tension in the strings if 50 grams is hung from the center of the meter stick? So there's 2 forces here now. The 50 grams, and also there's another force here of the weight, which was 0.1 G. Okay? And we'll call this force T and F. Yeah? Is this okay so far, guys? Yes?
I wasn't streaming. I was trying to. I finished the breakdown.
Oh, okay. This is number 5.
Yeah.
So, what can I say T plus F must equal?
0.050 G
Plus that one, yeah, so that'd be 0.15 G. Okay, now I need to make another equation. What should I look at next?
So,
Yeah?
about the first half question, it doesn't have the 50 grams left.
Oh, I'm sorry, I'm doing the second part, haven't I? Yeah, sorry, in the first part there is no 50 grams, thank you. So it's just 0.1 G. Okay, great. Now, how should I get the second equation? What should I do to get my second equation, do you think? I could look at... What could I look at? Maybe the turning force? Yeah? Where should I make my turning point? Where? Yeah, where do you say? Yeah, I'll put it right here at the T, okay? So, this one here, I only have one of them. What's the distance between here and here? And this is in the middle now. So if that's 0.10, how much is this? It's got to be 40 centimeters. Okay. And is it clockwise or anti-clockwise? Clockwise. Clockwise, yeah. Going this way around. Okay, and what's the distance from here to this guy? 4, and that's a 3. So it's a 7. So, and clockwise or anti-clockwise? That one is anti-clockwise. So you can say 0.4 times 0.1 G, that's supposed to equal 0.7 times s, that force.
What did you do before?
It's the distance from this turning point to here. And this is in the middle. It's its weight. It's a meter stick. Yeah. Is that okay? Yeah. So, maybe you can tell me now, the S is 0.4, 0.1 G over 0.7. We can have the S. 0.561 newtons. Now, if you put that into this equation, you can get T is 0.981 minus 0.561. So now I have my T.
$0.42.
0.42 newtons.
And you know it's meter stick.
Ah, you see, I was a bit sneaky because I said it's a meter stick. Yeah, tough all right out there. Are we ready for the next part? Ready for the next part? The only difference in the next part is you hang an extra weight here in the middle. So the effect of that is just to change its mass. Instead of being 0.1, it'd be 0.1 plus 0.05. So in part B, the only difference is it's T plus S equals 0.15 G. And then in the second part here, it's 0.4 times 0.15 G equals 0.7 S. The only difference. So again, the S will equal 0.4 times 0.15 G over 0.7. If somebody can get me that, that'd be great, please. Yes.
$0.841.
0.841 newtons, and then finally the T will be 0.15 G minus that answer you just got for S.
146.
146? Oh no. 0.15 G. Yeah, thought maybe something went wrong. tired, Siva? You look tired. What were you doing last night?
161.
0 point
631. 6305.
0.6305.
05.
Okay. So what were you up to last night?
Assignment.
Really? What assignments due today?
Not today, but we have the ICT and physics and now EAP.
I still remember.
You said yesterday.
No, not for engineers.
What ICT thing is this? What ICT thing
I
is
don't know,
this?
he gave us an essay and you have to correct it in reference to that thing.
Yeah.
What's this column?
Yeah.
Ah, yeah, the engineers don't usually do that.
Yeah, he told us.
Yeah.
It's not mandatory.
We have to do it.
Ah. Were you not listening to him?
We stress
I
them out.
remember
No.
he said you can do it either now or you can go home and do it.
No, you see, you can do it if you want to or not. And I decided not to.
Good decision. Alright. Are we ready for part C? Not yet? Okay. Mm-hmm. Are we ready for part C? Yeah? Matt, George? Yep. Siva? Yep. Okay. Part C. Right, so in part C, you have your meter stick, again. You have your string here, and your string here. And this is, what do we say, 0.1 meters. And this is 0.2 meters. Now, what happens in the last part, oh, and we have our weight here as well, which is 0, and that's a 0.1 G. In the last part of the story, I tell you that 50 grams, you move it somewhere. So, I don't know where to put it. I'll just imagine, like, which tension was bigger, the T or the S? The S was bigger, wasn't it?
Yes.
Yeah. So I feel like if I want to make these tensions equal, I'll have to hang my mass here maybe. Anyways, it doesn't matter. It doesn't matter where you draw it. Anyways, in the question I tell you that this force and this force are now equal. So where do I hang this guy? Alright? Now I'll just call the distance here to here, I'll just call it X, and I want to figure out what the X is. So do we understand the picture? Yes? Right. You sure? Even if you're sleepy, it's okay?
Yeah.
Right. So, what's the total forces going up? It's 2T. Oh, and going down, it's 0.15 G. Okay, well, I suppose I have the T at least, if that's helpful. 0.15 G over 2. Okay. But what I really want is the X. So next I'll use the turning force. So if I take this as the turning point, is this one clockwise or anti-clockwise? The other one. Clockwise, going around this way. Yeah. And the next one? And the last one? Okay. So the first one is X times 0.05 G plus 0.4 times 0.1 G, and that should equal 0.7 times T, which we know. We can put the T in. So we get 0.05 gx plus 0.04 g equals 0.7 times 0.735. So finally, my x will be 0.7 times 0.735 minus 0.04 times 9.81 over 0. Oh, but I did 0.4 times 0.1, so yeah. 0.05, 9.81. Which equals 0.25. So the total is 35 centimeters because you have to include this piece. So it's at the 35 centimeter mark. Oh. Okie dokie. What's next though?
Wait, how did you get 35?
35?
25?
Well, yeah, but the 25 is from the string, so it'll be at the 35 centimeter mark on the meter stick because we're at
Oh, yeah. Yeah.
yeah. What time do you sleep at, Siva? 1 a.m., 2 a.m., 2:30. My. And what time do you wake up at? 6. What are you doing up so early?
Shower.
6 a.m. How far away do you live?
I live like half an hour.
You get up at 6 a.m. That's amazing. Did you have class at 9? Okay. I live an hour and a half away and I don't get up at 6 a.m.
Because most of the time I find the bus is full, so I would have to walk.
Really?
Yeah, I have to get up early, like catch the bus early.
Which bus is this?
70, 39, 59, 80.
They're all full?
Yeah.
Really?
Yeah.
That's terrible.
Yeah.
You don't be walking home
Yeah.
in weather like
no,
this.
on the way back it's
Oh, it's only in the
nice.
morning,
Yeah, in the morning.
Yeah.
So I have to wake up before everyone.
That's rough, man. That's rough. Alright, what are we having a look at next now? Which one?
The rocket science.
Back to rocket science.
No, I haven't moved it.
Oh, okay. I still have it on the screen if you want me to go back to it. Do you want me to go back to it? Yeah. Which rocket science one?
5.
The last one?
H, right? Yeah, ish.
This guy? Can you make it out still? It was like this, Matt. Part in black I did first, part in blue I did second, and part in green I did last. That's the order, okay? Kim, Seba, do you have questions you want me to do? Yeah. You find ones you want me to do. Lammies.
Question 5.
Lammies. Ah, yeah. We're looking at Lammy next. Some people's page numbers might be a little different, yeah. Okay. Ready for this one? No, the last one on Lammies. Can I do this one now? Yeah. Okay. Right. We have a sphere. Oh, terrible circle. It's a little better. Alright, and we have a small wall here. And what happens is this is being pulled over the wall because there's a force right here in the middle pulling it along. Good grief. There we go. There's another force acting on this. Whoa, not that. The weight, obviously. What's the mass of this guy? 10. So there's a 10G here. But there is one more force I didn't draw. Now, just so you know, this is just about leaving the ground, okay? So don't picture it really touching the ground, like it's on the point of being lifted. So there's no reaction here, but there is another force.
The block.
Yeah, there's a reaction here, pushing.
That.
Yeah. Now, according to Lammy, there is one place that this must point. Where? Yeah, it has to point to the center, doesn't it?
Yeah.
Okay. So let's do a little bit of maths here. If I was to draw a line here, okay, how big is this distance to this distance? It says in the story the radius is 10 centimeters, so that distance is 10. How big is the wall though? It says 4. So if the total is 10, and this is 4, how big is this distance? 6. 6 centimetres, okay. Now, how big is this distance? How big is this distance here?
F squared.
No,
times G
no, no.
10.
10. Why? It's the radius again. So, if I draw a triangle, this side is supposed to be 10 and this side is supposed to be 6, we said. This is 6. And from using Pythagoras, this guy will be 8. Yeah? So can I know this angle? I can. I'll just call it theta. So this side here, this is or cos theta, and this one here is or sine theta. Now, actually, what is the theta, by the way? 36.87. Okay, so the up force, which is or sine 36.87, that should equal the down force. And the left force, or cos 36.87, that should equal the right force, which is F. So first I'll get or, and then I can figure out what F is. Right, so or is supposed to be 10g over sine 36.87. What's that, please? One.
16.5.
Okay. Now F is equal to, I said, or cos 36. So that's 163.5 cos 36.87, and then we have the answer. 130.8. Looks so easy now, doesn't it? What's next? How can we know the theta? Yep, it's tan inverse 6 over 8. Moments? Moments. Principle of moments. Moments. Okay. Which one? 3. Okie dokie. Let's have a look in a moment. There's a couple of people writing this down. Okay, are we ready for the next one? Moments now. Moments and centre of gravity. Okay, can I scroll down now? Number 3. A 40 kilogram girl sits at the end of a 3 metre long swing and a 100 kilogram father gives her a push. What is the moment force provided by the father? Okay, so there she is, and he gives her a push with a force of 100 newtons, and this distance here is, what is the distance? 3 meters. So the turning force is force by distance, which is 100 by 3. So the first part is 300 newton meters. Okay, that's okay. That's part A. Part B now. The girl and the father swap places, and the girl now pushes the father with 25 newtons. So the only difference is the force is now 25. So the answer then is 75 newton meters. Okay, part C. The girl sits at the end of a seesaw, which is 5 meters long. What is the turning force she's providing? So she's sitting at the end of this. So what force is she providing? It's her weight. Yeah?
Mm-hmm.
So the turning force, what's the distance? It's 2.5, because it's a seesaw. So, half of that is what you need for the turn here. And what's her weight? 40 G. So, whatever that is, please. 981. Okay. Now, if the father sits with her, the only difference now is the mass is greater. It's, what is it now? Is he 100? He's 100. So, yeah, what's that? 3433 Newton meters. Yeah? No? Well, my question was, what is his contribution? So that means I want to know how much extra it is. So if you subtract 981, do you get the same answer?
No, 2453.
2453. Yeah, okay. Is that okay? Yeah. E. E looks like it's the same. Sorry, I misread the question in part C. I mean, the answer's right, but I just want to draw the picture again. The father sits at the other end. So the girl is here, and the father is here. So what did we say her turning force was? It's 981 Newton meters. And his turning force would be 2453 Newton meters, the 100. Yeah. And in total, it's not, what did I say, 3 something. It's not this, because they're at opposite ends. So instead of adding, what should I do? Subtract them. Who's going to win? The father's going to win, and the net or the total will be the difference, not the addition. So the difference is 1472 Newton meters. So that's for the answer for C, D, and D. So she's C, he's D, and the total is E. D. D for dad. Right. Shall we do the last part, F? Yeah? Ready for F?
Yes.
Okay, no problem, no problem. Getting a headache? The weather?
Oh, I miss this so much.
You too! What time did you sleep at?
I don't remember.
Is it better or worse than 2:30?
5.
That's much worse.
5?
And you were awake at 6?
I went to bed
Yeah, but when did you wake up?
7.
Ah, that's terrible. Were you doing assignments? Assignments?
Yeah.
Yeah. Okay. Shall we do F now? F. So what happens in F is the two of them are at the end of a swing. And the angle here I said is 30 degrees and the distance is 3 meters. And they're obviously going to turn. Obviously turning. So I want to know what's the turning force. So the only force that they are really contributing is their weight, which is 140 G. But you realise some of their weight can be this direction and some of it will be this direction. This one here has no effect on making them turn. But this one here will make them turn. It'll make the swing go this way. So if we calculate the turning force as the force by the distance, we need to work out what this is. If that's 30, can you see that that's 30? So this one here would be 140 G sine 30. So the turning force is 3 meters multiplied by 140 G sine 30. And if you can give me that, that would be great.
Mm-hmm.
2060 Newton meters. That's okay. We'll leave the point 1 out. Okay. Right, so what's next now? Yep. What time are we at? Oh yeah, okay, yeah, go ahead. Right, what's next now?
How did you know you need to resolve?
Yeah, because you need the force and the lever to be perpendicular. And here, you know, if you didn't resolve it, then their weight and the swing, the lever, they're not perpendicular. I can only deal in perpendicular for turning forces. What's next?
Cantilever?
Huh?
Cantilever.
Cantilevers. Which one? 3. Okie dokie. Cantilevers, number 3. Ciao. You got that? Cantilevers next. Number 3. Cantilevers, this one.
Oh.
Okay. So, you've got our wall here. We've got our cantilever there, and we've got our string here. What do I tell you? A braced cantilever iron beam is supported by 13 centimetre stay. The stay is 5 centimetres above the wall. So how big is this side? This one here is 12 centimetres. But this beam is 15 centimetres long. So how much must this be? This must be 3 centimetres. And it's 20 kilograms. So here in the middle, there's 20 G. Now this is broken up into 7.5 centimetres and 7.5 centimetres. That 12 is from here to there, and that 3 is from there to there. There's another force. So we have this force. We have the force here at the hinge, and we have the force here, the tension force and the reaction force. Is that okay? Yeah? Will we get started now on this? So, if I draw a quick triangle here, 5, 12, 13, I can know this angle, which is this angle here. Can somebody give me that theta, please? This tan inverse 5 over 12. Thank you. Okay. So, look at the T. There's a force to the left and a force to the right. So you have here and here. You have T cos theta and T sin theta. And also for the OR, you have a force to the right and a force up. And I'll just call them OR X and OR Y. So the total up force is OR Y plus T sine 22.61 degrees. That's to equal 20G. And the force to the right, which is Rx, should equal the force to the left, which is T cos 22.61 degrees. I still need to make one more equation. I'll use this as my turning point. So I'll get 0.075 times 20G. That will equal 0.12 times T sine 22.61 degrees. Right, what can equation 3 give me? What can I figure out from equation 3? What can I get? I can get T, can't I? Yeah? Now, if I know T, what can equation 2 give me? Or X, because I already know T. And if I know T and or X, what can equation 1 give me? It can give me or Y. So let's calculate. So, T is 0.075 times 20G over 0.12 times sine 22.61. What's that?
Should be 319.
319 newtons. Okay, and the Rx will equal 319 cos 22.61. So what's the Rx equal? 294 newtons. And finally, I can get the Ry is 20G minus T sine 22.61. So, what's that, please? Or Y equals. Newtons. Yeah? So, my question was, what is the magnitude and direction? So I can answer it now. Here's the wall, and we know that there's a force Rx of 294, and there's a force Ry of 73.5. So how do we get the direction here? It's tan inverse that over that. So I hope that works out to be 14 degrees. Tan inverse 73 over 294. And the magnitude, how do I get the magnitude? Yeah, and then square root of that. So I really hope the magnitude then comes out to be 303 newtons then. Got that? Continue? Or do you need a minute to write this down? Yeah, no problem. Okay. Continue. Continue. The last part is the only difference in the last part is you hang a 5 kilogram mass at the end here. Okay? So that's a 5G. So let's look at the equations and just examine how they change. So that means in this equation, instead of being 20, that would be 25G. The total down is 25 now, yeah? Does this equation change? No, because it's left and right, no change. But this one will change, because now you have an extra turning force down in the clockwise. So if I just make a bit of space here, this is equation 3. Equation 3. There's an extra 0.15 times 5g. Because this was clockwise, clockwise, anti-clockwise. You had this guy now plus this guy should equal that one there. Okay, so really there's only a tiny, tiny change. This gets changed and this gets added in. But then everything else is the same. Everything else is done the same. Yeah. So I don't know if you need me to do it again, because I would just be doing the same thing here, except the numbers are a little bit changed. So for example, here this would be a 25, so that number would be different. Here this number would actually be the same. And then here it gets changed a little bit because the 319 is different, and also I have to include this value here. So I'd have to I'd have to change that. I have to add that in. I can do it if you like, or if you think it's not necessary, I can just leave it. What are your thoughts?
You can just do the same thing, like add these in with the difference.
Yeah, that's all. Yeah, that's all. Antex, do you mind getting that? Thanks. Oh yeah, you have to bring your umbrella. Oh, forgot about that. That's terrible. That's terrible.
Is it still raining?
What do you mean it's still raining? Look outside. Alright. What's next now? Kim, you have a question?
Power and efficiency.
Yeah, which one?
I got the answer, but
Yeah, which question?
7A, I got the ability to do it using AST.
7A, say again?
Like, I got the ability to do it using AST.
Ah, same answer or different?
Different.
Ah, let's have a look at it. Power and efficiency. An English teacher drives a 1044 kilogram Nissan Micra. Right, so distance is 4 kilometers, and it's the time is 17 minutes. So what's 17 times 60, please, Siva?
1020.
What is it? 1020. Yeah? And then here is distance, speed, time. So 4,000 divided by 1,020.
3.92.
What is it?
3.92.
Oh, 3.90. So that's the distance, that's the speed, and that's the time. That's okay so far? How much energy should the car require? So what type of work, what type of energy does the car have? It's kinetic energy, isn't it? Yeah, it's kinetic energy. It's a half m v squared.
0.92.
Oh, okay, 3.92. 3.92. Okay, so what is that then? That's 521 times. Okay, so whatever that is. Is it 8021? 8021 joules. Is that okay?
My question is I got the VAT.
Okay, what you say is U?
0.
V?
No.
Yep. A? T?
2020.
S?
4,000.
And what did you get for V?
7.8.
Ah. The problem is here. I know it's at rest. Really, in real life, you don't jump into a moving car. I know this. But for these problems, if I picture time and velocity, when you do it like this, you're imagining the car started at rest and very, 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 very slowly got up to its top speed. Whereas in real life, of course, you get in the car, you speed up, and then you go at a constant speed. So we are imagining the question is like this. It's a constant speed. But I get what you're saying, and that's fine. Do you understand what I'm saying here? In your situation, it means the car was accelerating slowly for the whole journey. So, both my picture and your picture are not like the real picture, but I feel like my picture is closer to the real picture than your picture. So this is the reason for it. Is that okay? Does that fix the problem for you? Do you need me to continue, or is it only? It's only this. Okay. Good question, though. Okay, what's next now? How are we doing for time? We've got a couple of minutes. We could do something else. We've got 4 minutes. If you can give me a question that's a 4-minute question, that would be perfect. You alright?
Yeah.
Okay. What's next? Huh? There's only 3 minutes left. You need a 3-minute question. Are we quite happy to leave it there for this afternoon?
Yes.
I think we're quite happy with this, yes. I won't see any of you after lunch, because you're going to get something sorted out in the bank, aren't you? Where do you have to go for that?
I'm going to AIB first because
In which branch?
no idea.
Is it like walking distance?
No.
No? Oh, okay. And you think they'll sort you out?
Hopefully, if not, then I'll go to the other one.
Which bank did you try to last time?
I didn't check.
Oh, okay. What bank did the other students use?
AIB.
Oh, so you're going in person?
Yeah.
See, okay, yeah.
When I went, they said I need like a PPS number or something like that.
Do you?
Like a tax station number.
Did they say you need it, or you could just use it?
No, I went to KBC.
Oh, KBC. Well, that may be different. I don't